This week, we're going to start a series of 3 weeks in which we talk about general methods for solving problems. So these are basically general approaches to ways that you can solve problems that you run into. And so in future weeks, we're going to talk about dynamic programming. We'll spend, I'd say, roughly think a week and a half on that, and a little bit about ways to search over solutions. But this week, we're going to look at two methods that are probably the most basic two, the two that you run into the most often. And you've probably thought of these before. One is what we would call a brute force method, and the other one are greedy approaches or greedy algorithms. So for both of these examples, there's not necessarily a very clear way to talk about approaching them. The two methods that we'll talk about later, there is more of a way to describe the method. For both of these, one of the big issues is just recognizing that you have a problem in one of these domains. And then there are some tricks that you can use, some techniques that help you deal with them. But again, the biggest thing is just seeing problems that fall into these categories and coming to be able to recognize them as you run into them. When is it appropriate to apply a brute force solution, or when do you need something else? And when is it appropriate to apply a greedy solution, and when do you need to use something else? So I'm going to start talking about brute force algorithms, and then at the end, I'll briefly talk about greedy algorithms. And I will just say, for those who have the textbook, I would strongly recommend looking at these sections of the textbook, because they provide several examples in there that I'm not going to have time to go through here. And I think it's useful to kind of look at the examples, because again, the more examples you see, the more you come to recognize this type of problem. So brute force is another way to think of it is a complete search. So the idea is that you are looking for an answer, and you're doing it by effectively examining every answer possible. Now, you don't really have to generate and look at every possible answer necessarily. In a lot of cases, you can get by with eliminating a lot of choices so that you don't really have to look at everything. But the idea is you're trying to hone in on the best thing by looking at every possibility. Now, many times, or at least sometimes, this is the only feasible solution. There's not another way. Feasible. I don't know if I spelled that correctly. But there's not necessarily another way to do something. So as a quick example, if you're given an unsorted list of numbers and you're asked to find what's the largest number in there, the only way to do it is to look at every number in the list. It's an order n operation. That's it. You have to look at every number in the list. There's no way to find the maximum or the minimum without doing that, since it could be at any point. Other times, brute force is going to be good enough. And what that means is there might be another way, there might even be a more efficient way, but brute force, the problem is small enough that trying every possibility is enough that you can check what's there. So as an example, if you need to compute something like n factorial different options. Okay, well, this might seem, and you need to find the best thing out of n factorial different options. That might just seem like, oh, that's infeasible. How am I going to do that? There might even be a very elegant way where you don't have to do all n factorial. But if n is small, and by small, maybe it's 3 or 4, or even all the way up to 8 or 9. Once you start getting 10 or bigger, that this n factorial just starts becoming a little bit too much, probably. But if you've got some fairly small number of n, then it's feasible to just generate all n factorial things and check them all. And it can often be easier to do that. It's faster to code. It still is within whatever time frame you need, and it's probably less confusing and less having to think about the problem and work through it to find some more elegant way of doing anything. And so very often brute force is usually, I'll say not always, but it is usually the easiest to implement. And that is one of the nice things that one of the nice things about it is if you implement with brute force, it's a simple way to use it to say, check to make sure that you understand how a problem works. You can use it to check a more complicated solution. So, maybe you have some other approach that you think is going to be great, and you can at least test it on smaller size problems by using the brute force approach. And then if it seems to work on those, you might have enough confidence that it will also work on the big problems. And so you can use brute force as an easy thing to implement, and then you can use it to check your more complicated solution, or you just use it to understand what's going on. Now, when we talk about brute force, there's kind of two ways that you can go about it, or there's, I should say, a couple of ways of categorizing brute force approaches. So one of them are what you might call iterative. And so this is where you tend to have loops to generate the possibilities. Okay, so you might have a series of nested loops. You might have I equals 1 to n, and then you might have j equals I plus 1 to n, and this might be n minus 1, and that might generate all of the various combinations that you have between any two numbers from 1 to n. So you're generating all the possibilities of picking two numbers, two distinct numbers from 1 to n out of a list. So that's one way you can do that, and that's an iterative approach using a loop. The other one that you run into is a recursive one, and this tends to work well when you have states. So a state is, if you learned about state diagrams and operating systems or something, the state just tells you what state something is in, and you make a transition to a new state, and you sort of want to explore all the different states. Usually you would want to do something like that recursively. And so you'll sort of make every possible choice. So if you're in one state, you try to make all the choices to generate all the new things. And then each of these is going to generate a new state. And then you would evaluate that state and so on. And eventually you would come to a solution about where things are. So there's two things about recursive approaches. One is you have to be careful of the call stack. So we've talked about this before, that you don't want to have too many recursive calls in a row. You sometimes want to make sure that you instead approach something iteratively. Maybe you keep a queue instead of actually making recursive calls. There's various ways to go about it, but it's something to be careful of. If there's a chance of making too many recursive calls, if you make 1,000 recursive calls in a row, that's not a good thing. If you're making 10, there's no problem. So you need to be careful of the call stack. And here you can use something called pruning. You can also use pruning in iterative approaches, but it's especially used here in recursive approaches, and we're going to come back to that. So that's one way of kind of thinking about the types of brute force approaches. One's the iterative, loop through everything. The other's recursive, kind of step through all the different options that you have at each stage. Another way that you can think of brute force methods are, you can think of ones that are generative. And so a generative method is going to actually generate valid solutions. So the idea here is that every time that you iterate through something, it's creating something, and that thing should be an okay solution. So you're just going to sort of go through and march through and just generate every possibility. And the other approach, kind of the opposite of it, is filtered. And this means that you, I won't use the word generate, I'll use the word create. You basically create everything possible and remove the bad ones. Okay, so later on when we talk about, there's some mathematical techniques, say for finding primes. One way that you can find primes is to use a sieve method, where you basically generate all the numbers and then you eliminate all the ones that are not prime, and then whatever's left over is prime. And that's an example of a filtered approach to generating primes, whereas a generative approach is going to actually try to say, what is the next prime that I could get? And there's not exactly a good way of doing that, but there's sort of things along that line. So generative methods try to just generate all of the different solutions directly. Filtered methods generate a bunch of stuff, including a bunch of stuff you don't want, and then filter out all of the bad stuff. Now, I already mentioned there's a few different themes that are here that you'll run into on when you're dealing with brute force methods. So one of them, the one that I mentioned before, is pruning. And the idea of pruning is that you stop as soon as you know that sorry, my writing doesn't keep up with my speech. Stop as soon as you know that something won't work. And while this might seem obvious, you often have to put special things in your code to handle pruning. So what this means is that, say you're doing a recursive method, that before you make another recursive call, you see, am I already in a state that is no good, that I know is not going to lead to the result that I want? Or if you're using an iterative method, you say, do I even need to keep doing this loop or going into the next sub loop? Or do I already know that this whole iteration is going to fail and I can just jump back to the previous one? So pruning is the idea of stopping this sort of pass through, stopping the brute force as soon as you identify that something is wrong. You just don't want to do work if it's not helpful. The other common theme that you'll see in brute force approaches is bounds check. And sometimes this is less obvious than others, but the idea is that if you have limitations on the on your input, on say the size of the input or the range of the input or something like that, it can lead to more limited generation of possibilities. Okay, so we'll see an example of this in just a minute. And so the idea of a bounds check is, if I know my bounds are only within some range, that can drastically limit how much of the space I need to explore. How many things do I actually need to try out? If I know, hey, I don't really need to go from 1 to 1,000,000 here, I only have to go from 1 to 1,000. That can obviously make a big difference. Okay, so those are two themes. We'll see them. We'll see a couple of examples here. Now, I will say on Wednesday, when we get to the coding examples for Wednesday's class, I'm going to code up an example that includes some pruning. I'll probably code a recursive n-queens algorithm just so you can see how that works. And pruning is a big part of that, so you don't keep going any farther than you need to. Now, let's say that we are limiting ourselves for the moment to iterative methods. So the idea on iterative is that we are going to generally loop through options testing each. And this can take a few different forms. There are ways that you can make your loops more efficient and so on. So I'll just sort of following on to things that we've said before. The first thing is that you want to use bounds check. So a bounds check is going to be the range of the loops. can be set. So you want to limit the range of each of the loops. So remember, if you have nested loops, they sort of the number of operations multiply with each other. So you want to handle that. You want to do some sort of pruning. And this is going to mean that you have, typically you'll have a flag to exit early. Okay, so you might have something that would be like for, I equals 0, and you'd say like is okay, and I less than n, I plus plus. Okay, okay, and so you have some sort of flag in here like this is okay, and you set that to true. And if at any point along the way you decide, oh, wait a second, this whole route is not going, you go ahead and you set is okay to false, and it lets you exit the loop a little bit faster. And you don't have to start messing with indices. I mean, you could end it earlier by just pushing I and resetting I to n, but that's kind of confusing to look at, and you can sometimes really mess yourself up by messing with indices like that. Okay, but having a flag along the way is an easy way to put something in. If you have a way to check and exit early, you can do that. And bounds check, I'll give an example here in just a minute of how this might work, is where we have you limit the range that each loop is going to take. As you're looping through, sometimes you want to generate all options. And I'll give you a couple of tricks that are here for doing this. So one of them is if you have a set of n items, okay, you can use an n-bit mask. Okay, so remember, a bit mask is when you have ones and zeros that indicate whether something is in there or not. Okay, so in this case, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so 8. So assuming that things are small enough, it needs to be small enough, you can then iterate through all of the numbers, all of the possible subsets. So you can generate all subsets by looping the bit mask from 0, let's say it's 1, 2, 3, 4, 5, 6, 7, 8, to 1, 2, 3, 4, 5, 6, 7. Okay, so basically if we count that in binary, and so let's see, 2 to the 8th, 2 to the 9th is what, 512. So this is like 512 different values here. Okay, so it's not that many, but I can generate 512 different subsets by just iterating through all the various numbers from 0 up to 1, 1, 1, 1, 1, 1, 1. Okay, and if you think of that, if each of those is a bit mask, you can then look and you can say what are all the different subsets. So in that case, if I had a set of n items and I wanted to generate all the subsets, I could do that. There is a command in C++. It is a useful one, and I'm not going to go through the details of it here, but I'll just mention it. It is called next permutation. And so I would recommend looking up that, look that up in your favorite C++ reference. That is an easy way of taking a bunch of numbers and just generating every permutation of those numbers. And it basically goes in a cycle. So if you start out with the numbers, 1, 2, 3, and I don't remember the order that it does these in, it'll then generate, say, 2, 1, 3, and 2, 3, 1, and it will generate 1, 3, 2, and 3, 1, 2, and 3, 2, 1. Okay, and again, I don't remember the actual order. There's a defined order that it generates these in, and it might be lexicographic order. So it might be 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. It wouldn't surprise me if that's the order. I just don't remember offhand. But anyway, look up next permutations. This is another way that you can generate all the different options of something, and you can kind of use some of the built-in tricks that the language provides you, either with a bit mask or with a function like next permutation, to do that a little bit more efficiently. Okay, so let me give you an example of how of a problem that you might run into. This is one that I pulled, I believe, out of the book that shows you how you can do a brute force solution for a problem. So let's say that you have a problem where you read in numbers A, B, and C. And we'll say that each one is less than or equal to 10,000. Okay, so we read in three numbers, A, B, and C, less than or equal to 10,000. And you are supposed to find distinct X, Y, and Z, all greater than 0, such that X plus Y plus Z equals A, and X times Y times Z equals B, and X squared plus Y squared plus Z squared equals C. Okay, and so the question is, can you find the numbers X, Y, Z that meet these conditions where you read in A, B, and C? And so this is an approach that you can use brute force for, and it is very doable to do it that way, but it helps to be able to limit some of what's there. So if we look at the problem, we know that these things, they're all positive numbers. They each, since A, B, and C are all within 10,000, I can just very quickly look at this and I can say, okay, I know that A, B, and C all have to be no bigger than 10,000 on their own. Okay, because I know that they have to add up to a certain amount. So I know that those all have to be less than or equal to 10,000. Now, I could do some sort of loop. I could say for X equals, sorry, I shouldn't have said A, B, and C. That's obvious that those are there. What I meant was X, Y, and Z are all less than that. So I could say something like for X equals 1 to 10,000, and for Y equals 1 to 10,000, and for Z equals 1 to 10,000. And notice that I could do that, but that is too many operations. So this is 10,000 times 10,000 times 10,000. And if I do and then here I check the three conditions. Now that would work, but going up to 10,000 is just not feasible. This is going to give you a time limit exceeded. So you can analyze this and you can say, well, maybe I don't actually need to do this. And if, in fact, if we look right here at C, if we look at this condition C, we can think about that a little bit and we can say, well, actually, our limits they can't go up to 10,000. That's actually not feasible. In fact, what we can say is that these are no bigger than 100. So this can be no bigger than 100 because 100 squared is going to be 10,000. And notice that since C is no bigger than 10,000, that means that X or Y or Z, none of those can be bigger than 10,000. And so we can reduce this to loops that go from 1 to 100, like that. And now already we've gone from something that was 10,000 times 10,000 times 10,000 to 100 times 100 times 100. And that's only 1,000,000 checks. And believe it or not, 1,000,000 is usually fast enough. You can do 1,000,000 checks. Chances are that alone would let this pass. But we can actually do a little bit better than that. So I'll just show you how we could do a little bit better than that. So there's another thing here, which is if I look here at line B, I know that the product of the three numbers has to be no bigger than B. And if B is limited to 10,000, well, what that means is that even if they were like all the biggest size, okay, if they were all the biggest size, then they all have to fall within the cube root of 10,000. And that's about equal to 22. Okay. And by the way, I think I could have, and I should have said this before. I don't think I needed this greater than 0. I think it's actually a more interesting problem if I got rid of that. And so this would be something like minus 100 to 100, minus 100, minus 100. And so this, instead of 22, you could say it's minus 22 all the way to 22. Okay, for one number. Okay, and so what that means is I could limit one of these to go from minus 22 to 22. Now, I couldn't do that for all of them, because if one of the numbers is smaller than 22, the others can get bigger. But like sort of one of them, can't be bigger than, that at least one of the three numbers has to be 22 or smaller, because if they were all greater than 22, then when you multiply them all together, you're going to get something bigger than 10,000. Okay, so that's what B would give you. Is it saying if all three are bigger than 22, then that's too much. Okay, so now I've already got something here that's going, and I will just erase it to make it clearer. We got something that goes minus 100 to 100. And we've got, again, minus 100 to 100. I will rewrite the whole thing. Sorry about this. You can say for x equals, and I'll just start with the 22, minus 22 to 22. And then the next one is we will say for y equals minus 100 to 100. And we will say for z equals minus 100 to 100. Okay, now believe it or not, we can do even a little bit better than this. Okay, so we did, even though this is all feasible right now, so that was about 8 million when it was all minus 100s. We just reduced that even more. We reduced it by basically a factor of 4 here. So we're down to about 2 million, or maybe even less than that. I'm not doing the math in my head very well. Anyway, this is all going down now to a very reasonable size problem, but we can do even better. And if we look at this first one up here, we can see, well, if we already know what x and y are, we don't actually need to iterate through z, because there's only one option that we need. So instead of looping through z, we can just say z equals a minus x minus y. Okay, and so now we've gone from something that originally we were looping from minus 10,000 to plus 10,000 in x and y and z. And we were able to look at each of the conditions on here, and we were able to reduce it a little bit further. So first of all, by looking at this condition for C, we were able to make the loop go from minus 100 to 100. By looking at condition B, we were able to reduce one of the numbers to 22 to 22. And then by looking at condition A, we realize we don't even have to compute one of the numbers. We don't have to loop through one of the numbers. We can just outright compute it, because once you've set x and y, there's only one choice for z. That's the only choice that's even possible. And so now we've still got a brute force solution, but this is a very, very fast solution. It's, what is that? 200 times 44, whatever 200 times 44 comes to, so 8,800. Okay, so less than 10,000 operations total to check every possibility and answer this question. So the point of this is to show you how you can take a problem that might initially look like a pretty big brute force problem, right? I mean, these numbers go to 10,000 and you have all the possible x, y's, and z's. But if you just analyze the problem, you can get it down to something that's a much smaller size. Okay, so that's what I wanted to say on iterative examples. I want to talk a little bit now about recursive problems. So a recursive brute force is where we are going to actually try to generate, or we're going to generate all the solutions. And this is often the recursive approaches are generative as opposed to opposed to filtered. So the filtering tends to be more like the iterative ones tend to be more filtered, and the recursive ones tend to be more generative, although that's not a hard and fast rule. And so typically here, the idea is that you want to prune quickly. So you need to prune as early as possible. Now, some of you might, if you have possibly ever seen something about, and this is a total side note, about alpha beta pruning in AI. It's a game playing mechanism for reducing the search space in a minimax tree. Alpha beta pruning is an example of doing this quick pruning to reduce a recursive operation. Okay, so that's just a side note in case you've heard of it. That certainly falls within this topic. Excuse me. So an example of this, and it's the one that I said I would code up on Wednesday, so I won't go into a whole lot of detail here, is what's called the 8 queens problem. And it's a classic problem in chess. And the idea here is that I've got a chessboard, and I'm probably not going to draw this very well, but okay, so there's my chessboard. It's 8 by 8. And the idea is, can I position 8 queens on the chessboard in a way that none of the queens can attack each other? So if, in case you're not familiar with chess, if you have a queen, the queen can move anywhere in the same column or the same row or on either of the diagonals. And so if you have a queen in some position, let's say right here, that queen can attack everything along a diagonal there and along this diagonal here and in that column and in that row. Okay, so that all of those basically are attackable from the queen. And so the question is, can I position 8 queens on the board, or maybe how many ways can I position 8 queens on the board so that none of the queens can attack each other, so that all 8 are put on the board and none can attack the other. So you can see if I put one where I had there and I wanted to put another one, well, maybe I could put one right here, because then they couldn't attack each other. That one, they're not in the same row or the same column or on either diagonal. But when I do that, it blocks off more squares and so on. Well, this is an example that's solvable via a recursive scheme. So if we wanted just the naive approach here, we could just figure how many possible ways are there to place 8 queens on a chessboard. And if you think of it, there are 64 squares on the chessboard, and we have 8 options there to choose from. So 64 choose 8, well, that's a gigantic number. There's no way we can generate all of those and test them very efficiently. And so what we can do instead is we can use a recursive approach. And the idea is we place a queen, and then place a second queen. And then you keep placing a third, and you do that all the way up until you place the 8th queen. And now, if you were to do this and you were to be totally naive, and the only time you ever checked anything was here after you'd placed 8 queens, well, guess what? You'd have to do all 64 choose 8 options there. There'd be too many options available to choose from. And so that's just not feasible. But what you can do is you can check at each point along the way, every time you place a queen, and see, is this a valid place? Is it possible for me to place a queen there? Or is there a way that I can limit the bounds that I have so that I'm not going to look at everything? So as an example, it's obvious that you don't want to place 2 queens in the same column or on the same row. Okay, and so let's just take columns. You can always say place your first queen in the first column, and you place your second queen in the second column and your third queen in the third column. That's already massively reduced the search space from what you had before, just by saying the first queen is in the first column, the second one's in the second, the third's in the third. And that it's just obvious, if you think about it, that you have to have 1 queen in each column is the only way this works. And likewise, every time you place one, you can check the row that queen is on and make sure that it's not conflicting with another one. And as soon as you have a queen and you decide, oh, I can't place that queen on a particular row, you immediately back out and go on to the next iteration. Okay, and so that's the idea of pruning, is by actually going through and checking and exiting early, and also checking the diagonals. You can leave earlier. So, like I said, I will go through an example of this in class on Wednesday so that you can see it all coded up. Okay, so I wanted to mention a couple of last few things about brute force before I talk about greedy algorithms. And so there are some ways of speeding things up. And so in addition to everything that we've talked about before, there are all sorts of source code optimizations that you can do. And occasionally these are the things that you need to make a brute force method fast enough. And this could be everything from faster IO, the things that we talked about not making too many system calls, or using a faster language like C++ instead of Java, or Java instead of Python. It could have to do with allocating memory. So it generally is helpful to allocate memory statically rather than dynamically. So if you can know the maximum size of something and just allocate it at compile time, that's going to be faster than doing dynamic memory allocation. If you use bit manipulation, that's a whole lot faster than doing indexing. You can sometimes store your arrays in a row major order so that you can access them more quickly. So that as you're running through them, everything will be in cache where you want it to be. So there's a lot of like little code speed ups that you can do. And sometimes these will make a difference. Like the input reading, if you have to read and write a lot of input, then the fast IO really does make a difference. And sometimes the language really does make a difference. The other things about allocating data, usually it's only if something is right at the borderline that's going to make a difference. And typically that's not where the biggest thing comes in. But I'll just mention source code optimizations can play a big role in doing brute force. Another thing you can do is you can sometimes pre-compute data and then hard code it. Okay, or you can think if you're not in a like contest type environment, you can read it in from a file. And so the idea is, rather than spending your time computing a bunch of stuff during runtime, if you pre-compute it and just read it into an array or have it hard-coded as an array in your code, then it's just there, it's automatically in, and you don't have to spend any time at runtime pre-computing those things. So especially if there's stuff you can pre-compute, if there's stuff you can figure out ahead of time that is independent of the particular input that you need to process, but something that you need to have in order to figure it out, doing a pre-computation can really potentially save time. There are other times when you can use symmetries. Okay, symmetries, if you think back to the iterative problem that I showed before, like plus and minus are the same thing, or A, B, and C, or sorry, X, Y, and Z in that problem that I gave before are all interchangeable, so it doesn't matter which one is which in there. So because you've got sort of all these symmetric options, it lets you limit the range that you're doing. Now, sometimes using symmetries, it takes more overhead because you have to actually figure out what they are and work through all of them. It can sometimes not help. But if you ever notice that, oh, I can reverse the order of these two things, or it doesn't matter if these two things are in this order or that order, or every possible combination of A, B, and C would work. So I get, I can get 8 times as many things, but I only have to solve for one of the 8. That can sometimes, if either one can be like yes or no, there's 8 different options then, right? And the only thing you might need to code up is one of those particular 8 options, and then you just use that to generate the other 7. So sometimes symmetries can actually help you speed things up. Another thing, I mentioned some of the other stuff earlier about pruning and about doing bounds check and stuff like that. Even simple things like in an if statement, making sure that you put the thing that you expect to encounter the most commonly to exit your loop sooner. If you put that first in the condition check, then that's the one that will exit quicker rather than doing something that's likely to pass every single time. Okay, so one other thing is occasionally it is helpful to I'll say solve backward. And there's a nice problem that's mentioned in the book about this. So I'll just give you an idea of what that is. So sometimes you have to just think of a problem in the reverse order. So imagine that you have a problem where you're given a grid, and this is a rat problem. So you're given a grid of, say, city streets, and there's rats at various points in the city, at various intersections. And you know where the rats are, and you want to find what is a good location for a rat poison or rat bomb or something. And so a rat bomb might cover some area, maybe it covers like a 3x3 area or something like that. And you're going to kill all the rats in that area. And you want to say, what's the best spot for me to put this rat bomb to kill all of them? And that problem, I mean, one way of doing it is you could take this sort of green square and you could test out every single location. I could say, well, I'm going to put it there, and then I'll put it there, and then I'll put it there. And you could run through and do everything. And that's likely to take way too much time. And what you can do instead is you can solve kind of the inverse problem. And you can say, okay, for one rat, like let's say this one down here, for that rat, where are the locations where a bomb would kill me? And a bomb would kill you if you're within 3 of it. So you would mark each of the places where a bomb is, where a bomb could kill you. And then you go on to the next one, and we'll say like this blue one, and you let it mark each of the locations where a bomb would kill it. So if a bomb is in any of these locations, it'll kill that rat. And if you do that for all of the rats, then like let's say that the bomb has an area that's a D by D area. So what that means is there's going to be D squared things to check for each bomb. And let's say that there are R rats. Okay, then you have R, because each rat is going to have to fill in D squared different points that it lists. Whereas the other way around, if you have a grid, and let's say that the grid is n by n, then you would have something that's n squared D squared, and then you'd have to check for the number of rats in each one. So if the first method that I talked about placing the bomb at each location would be n squared D squared, and the other one is R D squared, and chances are R is going to be way smaller than n squared. And so this approach is quite feasible, and this approach might be completely infeasible. So sometimes trying to think, can I reverse the way I think about a problem so that I still do a brute force check, but I'm doing a brute force check on kind of the inverse of the problem that I care about, will be enough. Okay, so all of that is a summary of brute force approaches. Again, it takes just some experience to deal with them. Even more so, I want to briefly mention greedy approaches. Now, I think everyone is familiar with the idea of greedy algorithms and what it means for an algorithm to be greedy and for it to work. Just as a reminder of how this works, the idea here is you do what seems best at the moment. Let me rewrite this. Okay, so you're not actually trying to find like look ahead at every possibility in the future. You're just going to say, I'm going to do the thing that looks the best right now. And if you keep doing that, then you're always going to, hopefully come out with what the optimum is. Now, this works. If you remember your 411, it works in 2 conditions. So you have to have 2 things. One is what's called optimal substructure. And what this means is that after taking your greedy choice, so after making the greedy choice, you are left with a smaller problem, or sometimes smaller problems. of the same type. So basically you make a greedy choice and then you say, okay, now I'm left with this thing that's a little bit smaller. And again, you should be able to use the same thing there. So that's the optimal substructure. The other one, and I'll just say, to me, this always bothered me, is what's called the greedy property. And this is like, well, a greedy algorithm works if a greedy algorithm works. That's the way I usually interpret it. Now, you can actually say, like, actually proving that something has the greedy property. There are ways of doing it that there's a reason it's called that way, but at least the initial thought is, hey, a greedy algorithm only works if a greedy algorithm works. So it's like, what does that mean? And that's when I said that you have to just sort of recognize these things. That's part of what I mean. But really what the greedy property means is that your greedy choice is no worse than any other. So you don't actually have to show that it's better. You just have to show that it's no worse than any other. And kind of what that means is you haven't eliminated something better. Okay, so so the greedy choice not being any worse than any other one is sort of the way to go about things. You say, okay, well, I know that if I do that, I haven't made my life worse. There's not a way that someone could have done something like taken some other choice that clearly would mean this one was a bad choice. This would still be just as valid as before. If that's true, then it has the greedy property. I will just mention it can be really, really tough to like formally prove this, especially if you have any time constraint, like you tend to in a programming contest or something like that. So the greedy property, it's often, the idea is not to necessarily prove it, it's just to recognize it when this sort of thing happens. So for those who have the book, I would really, really recommend you look at the book. I'm just going to give a couple of very quick examples of greedy problems here, but there are a couple more that are in there. So one of the most famous ones, so they're kind of what you would call classical greedy problems. They're like the greedy problems that people think of. So one of them is scheduling. And you've probably all heard of scheduling because it's the most commonly used one. The idea is you have jobs with a fixed start and end, and then how many can you do? Okay, and so if I think of each job as, I've got a job here that starts at this point. So imagine that this direction here is time. Okay, and so each job that I show you, it's going to have kind of a different time that it can be done. And maybe there's one there, and there's one there, and there's going to be one here. And there's going to be one here. And there's one there. And there's one that. Okay, so anyway, there's a few different jobs. I wasn't thinking through as I did these, but there's different greedy approaches that you can work, and there's some that do not work. So there are some that are not good greedy approaches. So an example of one that is not a good greedy approach is pick the first to start. Okay, so if I look at the one that's first to start, it might be this one on the bottom. And obviously, if I do that one, I can't do any others, right? That's the only one that can be done. If I'm working on this job the whole time, this one on the bottom, there's nothing else that can get accomplished at that time. So that's not good. I don't want to do that. So no good. Don't do that. Another one that might be tempting is you might want to always pick the shortest. And in this case, that might actually work. I don't know. In this case, the shortest one would be that one. So if I pick that one and then I pick the next shortest, it's probably this one here, and the next shortest is there. And actually, I think that is optimum in this particular case, but you can pretty easily come up with ones that are the shortest ones possible that would block things. So imagine that I had one, imagine that each of these was just a little longer, and I had a nice short one that was right there. And somehow if I select this one, it's going to block both that and that and that and that and that and that. And pretty soon I find I can only get this short one and maybe one other short one, and none of the others are there because they get blocked by it. Okay, so picking the shortest one does not work. Another one that you might think is pick the one with the fewest conflicts. Okay, so you might say something like, well, I'm going to pick one that only conflicts with, maybe one other one. And unfortunately, there might be other reasons why you wouldn't want to do that. So, I could imagine having one here, and it might only conflict with, let's see, well, let's just say, it might only conflict with, say, two things. Now, actually, I'm having difficulty coming up with one of these right now, but there's definitely cases where that is going to be a problem. And there is one that works well. There is a greedy choice that works well. So yes, is you pick the one that ends soonest. Okay, so the first one to end. So if we look at this example up here, this is the first one to end, and then that's blocked a few other ones. And then I look at the next one to end of everything available, it would be that one. And then I look at the next one to end of everything available, and it would be that one. And so I could get 3 jobs done in that case. And so that's an example of there are good greedy choices, there are bad greedy choices. Just because it's a greedy problem doesn't mean that every greedy choice is equivalent. But if you think through, you can pretty easily convince yourself that, oh yeah, this makes sense, that this is what's going to work, because if you always pick the one that ends first, remember what the greedy choice means. It means it's not you haven't eliminated anything clearly better. And so by picking the one that ends first, there's nothing else, like you haven't eliminated anything that another one wouldn't have also eliminated, because all the others would go longer. And so if anything, they eliminate more of them. They couldn't eliminate any fewer than you did. And so you know that that's good for now. And then you take what's left over and you've got a new problem that's smaller. It's got optimal substructure and so on. Okay, so scheduling is one of these kind of classical problems. Another one is coin change. So the idea is given coins with certain values, you want to give change for a certain amount of money with the fewest coins. And this one is greedy for some value combinations, but not for others. Okay, so some combinations of coins, taking the biggest one at a time, which is the typical greedy choice, is not going to lead to the smallest amount or the fewest number of coins that are given in return. And so one of the kind of classical examples here is if you have like coins of value 4, 3, and 1, and you need to make change for 6. The optimum is to use 2 coins of 3, but if you pick the biggest coin, you would do 4, 1, 1, and obviously that's not going to be as good as that. So this is one where greedy does not work. Greedy does not work with that combination, but there's plenty of other combinations where greedy does work. A simple example would be if everything is a multiple of the one below it. So if you have 1, 5, 10, and 100, Well, clearly you pick the hundreds, and then you pick the tens, and then you pick the fives, and so on. Okay. Finally, I'll give you one more. And again, I would say if you have the book, look at the book, because it's got probably 5 or 6 examples of greedy algorithms. It's got another 5 or 6 of brute force that we didn't go through here. And it'll give you a much better sense of the types of things that you can run into. But another one here is a bipartite matching. And so the idea of bipartite matching is you have sort of 2 lists here, and you're wanting to, and sort of these are the things that you have, and these are the things that you need, and you somehow want to match the things that you have with the things that you need. And so the idea is you always try to match the smallest one here, the smallest have, with each of the needs. And if you do that along the way, you can get kind of the optimal matching. You can meet as many needs as possible with what you have along the way. If we have time on Wednesday, I will go through an example of this. If we don't have time, I will just give you a hint now. If you look up the problem, it's on Caddis, called The Dragon of Blue Water. And by the way, if you see things like Blue Water, that's Waterloo University. They're probably one of the top universities in Canada, if not the top university, certainly one of the top few. In competitive programming, they're extremely good, and they have had a long history of problems. So you'll see Waterloo related problems along the way. Anyway, look up The Dragon of Blue Water. I will probably do it on Wednesday if I have time, but I'm not sure if I'll have time to code it up after I do the N queens. Okay, so that's all I wanted to say about greedy algorithms. So we talked about both brute force and greedy algorithms. Those are going to be the theme for this coming problem set. Again, I would recommend that you look at the textbook. If you have it, the sections in the textbook are 3.2 and 3.4. Next week, we are going to talk about dynamic programming, which is 3.5. And then the week after that, we'll probably still talk a little bit about dynamic programming and also talk about 3.3, which has to do with searching. So I will see you then.